Step 1 of risk management generates a comprehensive list of potential risks. However, not all risks are created equal. Some pose minor threats and can be safely disregarded, while others have the potential to derail the project. Project managers need a method to prioritize these risks, separating the inconsequential from the critical. This will be our focus in this video. Scenario analysis is a popular and straightforward technique for risk assessment. Here, the team evaluates each risk based on how probable an event is to occur and how much damage it could cause if it did occur. For example, while a project manager being struck by lightning might significantly impact the project, the likelihood is so low that it's not a major concern. On the other hand, employee turnover is a common occurrence with potential negative consequences. In such cases, proactive measures like staff development or retention incentives can be implemented to mitigate the risk. To ensure a credible risk analysis, the project team needs to define different levels of probability and impact. These definitions should be tailored to the specific project. For instance, a simple scale of unlikely to highly likely might suffice for a smaller project, while a larger project might benefit from a more precise numerical scale. For example, 10% equals unlikely, 50% equals likely. Defining impact scales can be more complex, as different risks affect project objectives in varying ways. For example, a component failure might cause a minor schedule delay but a significant cost increase. If cost control is a top priority, the impact is severe. However, if time is more critical, the impact might be considered moderate. Because impact is ultimately judged based on project priorities, various impact scales are used. Some utilize simple rankings like low, medium, and high, while others use numerical values. Scales may also focus on the overall project or specific objectives. The risk management team needs to establish clear definitions for these impact levels upfront. Here's an example of an impact scale commonly used in project risk management. This scale considers the potential consequences of a risk event on the 4 core project objectives: cost, schedule, scope, and quality. For each objective, the impact is categorized based on the severity of the consequences. Negligible. The risk event has minimal or no effect on the project objective. Low. The risk event causes a slight deviation from the project objective, but it can be easily managed. Moderate. The risk event causes a noticeable impact on the project objective, requiring corrective action to get back on track. High. The risk event significantly impacts the project objective, potentially causing delays, increased costs, or a reduction in quality or scope. Severe. The risk event has a devastating impact on the project objective, potentially jeopardizing project completion or success. This is a basic example, and the specific wording and number of categories can be adapted to fit the needs of a particular project. Some projects might benefit from a more granular scale with additional impact levels between moderate and high. Documentation of scenario analyses can be seen in various risk assessment forms used by companies. This graphic is a partial example of a risk assessment form used on an information systems project involving an operating systems (OS) upgrade. Notice that in addition to evaluating the severity and probability of risk events, the team also assesses when the event might occur and its detection difficulty. Detection difficulty is a measure of how easy it would be to detect that the event was going to occur in time to take mitigating action, that is, how much warning there would be. So in the OS upgrade example, the detection scale would range from 5 equals no warning to 1 equals lots of time to react. Often, organizations find it useful to categorize the severity of different risks into some form of risk assessment matrix. The matrix is typically structured around the impact and likelihood of the risk event. For example, the risk matrix presented in the graphic consists of a 5 by 5 array of elements with each element representing a different set of impact and likelihood values. The matrix is divided into red, yellow, and green zones representing major, moderate, and minor risks, respectively. The red zone is centered on the top right corner of the matrix, high impact/high likelihood, while the green zone is centered on the bottom left corner, low impact/low likelihood. The moderate risk yellow zone extends down the middle of the matrix. Since the impact is generally considered more important than likelihood, a 10% chance of losing $1 million is usually considered a more severe risk than a 90% chance of losing $1,000. The red zone, major risk, extends farther down the high impact column. Using the OS upgrade project again as an example, interface problems and system freezing would be placed in the red zone, while user backlash and hardware malfunctioning would be placed in the yellow zone. The risk severity matrix provides a basis for prioritizing which risks to address. Red zone risks receive first priority followed by yellow zone risks. Green zone risks are typically considered inconsequential and ignored unless their status changes. Failure mode and effects analysis, FMEA, extends the risk severity matrix by using the equation risk value equals impact times probability times detection. Each of the three dimensions is rated according to a 5-point scale. For example, detection is defined as the ability of the project team to discern that the risk event is imminent. A score of 1 would be given if even a chimpanzee could spot the risk coming. The highest detection score of 5 would be given to events that could only be discovered after it was too late. For example, the system freezing. Similar anchored scales would be applied for the severity of impact and the probability of the event occurring. The weighting of the risks is then based on their overall score. For example, a risk with an impact score of 1, with a very low probability of 1 and an easy detection score of 1, would have a total score of 1 times 1 times 1, which would result in an overall score of 1. Conversely, a high-impact risk that is highly probable and impossible to detect would score a 5 times 5 times 5 and result in an overall score of 125. This broad range of numeric scores allows for easy stratification of risk according to overall significance. FMEA is a systematic method used to identify, analyze, and prioritize potential failures within a system, process, or design. It provides a more comprehensive approach to risk management by considering additional factors beyond basic probability and severity. Project managers can leverage statistical techniques such as decision trees and net present value variations to effectively assess and manage project risks. Decision trees help evaluate alternative actions by calculating expected values, allowing comparison of potential outcomes. Net present value variations assess cash flow risks by analyzing correlations between past projects' cash flows and S-curves, aiding in financial risk prediction and management throughout the project lifecycle. Program evaluation and review technique, PERT, and PERT simulation are crucial for assessing overall cost and schedule risks. PERT focuses on the likelihood of completing the project on time and within budget, while PERT simulation enhances this by using statistical distributions for activity durations and running multiple simulations. This results in a criticality index indicating the probability of activities becoming critical and identifies potential critical paths and their probabilities. These tools enable project managers to make informed decisions, allocate resources efficiently, plan for contingencies, and increase the likelihood of project success. These advanced techniques are beyond the scope of the current course and will be studied in future courses on advanced project management.